Okay, in this lesson we'll learn a new test for convergence, and let's start by reviewing. Here we have a sequence and here we have a series, so we know that the harmonic sequence converges to 0. That converges. This is the harmonic series and it diverges. And we could show that with the integral test or with the P-series test. But let's look at what's happening here. We have a harmonic series, but now we have this -1 that's going to alternate. As we put an odd number here, we get a negative. We put an even number here, we get a positive. So let's see what happens with this. -1 to the 1 over 1, we have -1. -1 squared over 2, we have +1/2. -1 cubed over 3, we have -1/3. So now we can see the harmonic sequence, and it's just going to alternate. The signs are going to alternate. So now we go to +1/4, -1/5. Then let's look at the sequence of partial sums and see what's happening with that. If we add these two, then we get -1/2. If we add all three of these, we have -5/6. Here we have -7/12. If we add all of these, we get -7/12. If we add all of these, we have -47/60. And to graph it more easily, let's say this is 0.83, 0.583, 0.783, and that's a negative. Yeah, let's just graph it over here. So we go at 1, we'll be at -1. At 1, we go to -1. At 2, we go to -1/2. At 3, we go to -0.83, somewhere down there. At 4, -5.83. And we go to. So it is converging toward some value right there, somewhere between -0.6 and -0.75, somewhere in there. But we can see that it is converging, and that leads us to the alternating series test. This harmonic series diverges, but once we start making the sign alternate, then it's going to converge. If the sequence is positive, if the limit of the sequence is 0, and the sequence is decreasing, if all of these are true, then the series converges. So we have positive values, we have the limit being 0, and it's decreasing. we have something called absolute convergence, and that is the series converges without this, without alternating, and then all right, absolute convergence means it converges if you ignore the -1 to the end, and conditional convergence, it requires that the -1 to the end is there. Another way of saying this is the sum of the absolute value of the sequence. So the absolute value gets rid of the negative, and then we could just see it would have to converge without the negative. All right. Does this converge? And we have to look at the conditions. It has to be positive. The sequence n to n minus 1, this has to be positive, ignoring the -1. So we do have positive values there. And let's just look at some values of the sequence. And we'll say an. The sequence is just 2n, n over 2n minus 1, ignoring the -1. Let's see what these values are. You put a 1 there, put a 1 there, and you get 1. And then we'll have 2 over 3, 3 over 5, 4 over 7. We have positive values, and we need to have, so we say that the sequence has positive values. Let's see what happens to the limit. All right, as n goes to infinity, we get infinity over infinity. So with L'Hopital's rule, we have 1 over 2. We take the derivative of n and the derivative of 2n. All right, so there's the problem. The limit is not 0, so can't use alternating series test. But we have 1 condition, 2 conditions, and the third condition was decreasing. All right, so we just stopped there on the second condition because it wasn't satisfied. Okay, see if this converges. Pause the video and check the 3 conditions. All right. Are the terms of the sequence positive? If we put a 0 here and a 0 there, we're going to have a value of 0. So we could say We could just start at 1 if we wanted to see what happens after that. So here's a little problem. If we put a 1 in there, then they're positive. If we put a 0, then there's a 0 value. We could get around that, but let's check number 2. We have the limit. That's infinity over infinity. So we'll do L'Hopital's rule. And that's not equal to 0, so we can't use the alternating series test. Okay, pause the video and try that one. So let's see what's happening to the sequence. If we put a 1 here, that's positive. Put a 2 there, that's positive. We have a 1 on top, so we know it's positive. The sequence is positive. What's happening to the limit? What is the limit? And when I wrote it, I wrote absolute value, and all that does is gets rid of the negative 1. So if we wrote it like that, it's the same as writing this. As n goes to infinity, natural log goes to infinity, so that equals 0. Remember, the graph of natural log is like this. Its y value is going to infinity. So that satisfies the second condition. And then we have to look at, is the sequence decreasing? So we'll look for the derivative. Let's say f of x equals 1 over ln x plus 1. And we'll find the derivative. We want to know if the derivative is always negative, and that means the sequence is decreasing. So denominator times the derivative of the numerator, derivative of the denominator, so we have 0 minus that, so we have negative let's write this with the square on the outside. Here the derivative of natural log is 1 over x plus 1, so we have that. We could rewrite it as negative 1 over x plus 1 and let's see, is this always negative? Well, the x values, x is always positive because n starts at 1 and goes to infinity. That's positive. So here the x is doing the same thing. So this is positive and we'll have a negative. And this is always less than 0. So it means that the sequence is decreasing because the derivative is negative. All right. And so we can say, based on the test, based on these 3 conditions, therefore, the series converges and we're going to say conditionally, because if it didn't alternate, this diverges. If it didn't alternate, it would diverge. Because it's alternating, it converges. So that means it's conditionally convergent. Alright, pause the video and check that one. Alright, is the sequence positive? Well, if we start at 2 and put a 2 there, we have a positive there. Let's ignore that and see what's happening with the sequence. If we put a 3 there, we get positive, so the sequence is positive. What's the limit as n goes to infinity? 1 over n minus 1. The limit is 0. And then we just have to see that the sequence is decreasing. So we want to check this function to see if its derivative is negative. Oops. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So that'll give us negative 1 over x minus 1 squared, which is negative. So we know that the series converges conditionally because without alternating it would diverge. Alright, so that's conditionally convergent because the 3 conditions are met and it converges. Alright, pause the video and try that one. First thing we check is, are the terms of the sequence positive? Put a 0 there and we get a 1. Put a 1 there and we get a 2. They're all positive. We need to know if the limit of the sequence is 0. Yes, because the denominator increases. And now we check to see if the sequence is decreasing. So we're going to look at let's find the derivative. And we just copy. We do the chain rule, ln of the base. We have negative natural log 2 to the negative x. And this is always positive. Here we have a negative. So we know that this is always less than 0. The derivative is negative. And that's going to tell us that the sequence is decreasing. And we can say that this series converges absolutely because without alternating, it also converges. This is a geometric series, a convergent geometric series. It will converge whether there's an alternating sequence or not. The -1 is not required for convergence. Alright, pause the video and try that one. Alright, as the sequence positive, ignoring the -1, we put a 1, a 2, a 3, they're all positive. The sequence values are positive. Let's look at the limit as n goes to infinity. Here the denominator will go to infinity, 1 over infinity, we get 0. Then we have to see if it's decreasing. Is the sequence decreasing? So we check 1 over x radical x. Let's write that as x to the 1, and that's x to the 1/2. So we have x to the 3/2. And then write it as -3/2, and we'll do the derivative. Subtract 1, we get -5/2. So we can rewrite that as -3 over 2. This will be 1 over x to the 5 over 2. We're only using positive numbers anyway, so this is positive times a negative. That's less than 0. The derivative is negative, so the sequence is decreasing. We know it converges, but does it converge conditionally or absolutely? We have to consider what is happening to this. So n times radical n, that has a degree of 3/2, and this is a convergent p series because 3/2 is greater than 1, and we'll say that this converges absolutely because the series converges on its own without alternating. All right, and when you do this one, remember to rewrite that as a fraction. That'll be easier to see. Pause the video and try that. Negative exponent, we're going to put that in the denominator. And now we look at, is the sequence positive? A graph of the exponential will always be positive. So yes, it's positive. What's the limit as n goes to infinity of 1 over e to the n squared? The denominator goes to infinity, so that is 0. And then we'll look at the derivative. We have f of x equals, and let's write it like this without the alternating, e to the negative x squared. The derivative is, we'll copy, chain rule, ln of e is 1, so we don't have to write the ln of e. And here we have negative 2x over e to the x squared. E to the x squared is always positive, so we have a negative. X is always positive because we're looking for 0 to infinity. So then we know that this will always be negative. And that means the sequence is decreasing, so we can say that the series converges. Does it converge conditionally or absolutely? So we have to check what's happening with when it's not alternating, what's happening. So here we could say this is, it's going to converge, and that would be a direct comparison. We could do a direct comparison test, but that converges. So we say the alternating series converges absolutely. Because this series converges, meaning it converges without alternating. Alright, and that's the end of this video.